Today we're going to look at a really interesting object known as the Q analog of the factorial. But in order to work some clickbait into this, we're going to call it the quantum factorial. But sometimes it's called that anyway. But before we look at exactly what that is, let's recall some basic facts. Maybe all of this is going to be built off of the fact that n factorial, which is equal to n times n minus 1 times n minus 2 all the way down to 1, the descending product, is equal to the number of permutations of the set containing n elements. And we might as well call that set containing n elements all of the natural numbers 1, 2, 3, all the way up to n. So as a quick example, 3 factorial is 3 times 2 times 1, and it's pretty easy to enumerate all of the permutations of 1, 2, 3. Let's notice we've got 1, 2, 3, we haven't changed anything. Here we've swapped 1 with 2 to get 2, 1, 3. Here we've swapped 2 with 3 to get 1, 3, 2. Here we swap 1 with 2, 2 with 3, and then 3 with 1, or vice versa. And finally, we've got this 1 down here, 3, 2, 1, that we attain by swapping 1 with 3. Okay, so now that we've recalled this, let's work into this quantum factorial, or the Q analog of the factorial. But in order to do that, we need the Q analog of the natural number n. And we can motivate that with the following very, very simple equation. So n is clearly equal to 1 plus 1 plus 1, all the way up plus 1, where this addition is happening n times. Okay. But we might as well rewrite this as the limit as q approaches 1 of 1 plus q squared, ending at q to the n minus 1. Notice that's a sum of n objects, and each of them limit to 1 as q approaches 1. But let's notice that that is a finite geometric series, so we can apply the summation rule for a finite geometric series, and we'll get the limit as q goes to 1 of 1 minus q to the n over 1 minus q. And this object right here will be our Q analog of the natural number n. And so we might as well introduce some notation. So just continuing this limit, this is the limit as q goes to 1 of, I'll call this bracket n sub q. So that's the definition that I'm making here. That is the Q analog of the natural number n. So maybe I will box each of these in green and just put an arrow from one to the other and say that that is my definition of this object right here. We'll put a star there to say that we're defining this star boxed object in terms of this other object. Okay. So now we've got this Q analog of the natural number n, and we can define all sorts of things. So since we're going to focus on the Q analog of the factorial, we're going to jump to that definition. So we'll use this notation. We'll have bracket n sub q exclamation point. So that's our Q analog of the factorial. And we'll define it just as we define the factorial, and that is as the descending product. But instead of descending products of natural numbers, it'll be descending products of Q analogs of natural numbers. So that means we'll have the Q analog of n times the Q analog of n minus 1, all the way down the Q analog of 2 times the Q analog of 1. Now we could expand this out if we wanted to. So this will be 1 minus q to the n times 1 minus q to the n minus 1, all the way down 1 minus q. And this is occurring over 1 minus q, all of that to the n power. So that follows very, very quickly from this green boxed definition that we constructed. Okay, good. Now let's see what the Q analog of the factorial counts, if indeed it counts something related to the partitions. And we'll do it with this example that we've just started. So let's look at the Q analog of 3 factorial. Okay, so that'll end up being 1 plus q squared times 1 plus q. And so I did a little bit of simplification from this stuff over here, but that's not a big leap. But now we can multiply this out fairly easily, and we'll get 1 plus, let's see, we'll have q times 1 and q times 1, so it'll be 2 times q. And then we'll have 2q squared terms as well, so plus 2q squared plus q cubed. Okay, so that's our q analog of 3 factorial. Now let's see if that has anything to do with this down here. So in fact, the coefficients of certain powers of q right here correspond to permutations with that number of so-called inversions. So let's talk our way through it. So this permutation 1, 2, 3 has 0 inversions. And that's because none of these numbers are out of place. They are in their original order, where here we're taking the canonical order to be 1, 2, 3. Okay, and then notice that each of these have 1 inversion. So, and let's maybe talk our way through that. That's because here we've swapped 2 with 1. So 1 and 2 are out of order. And whereas in the second one, we've swapped 3 with 2. So 3 and 2 are out of order. But in this one, 3 is in order and 1 is in order. So that's why we only have 1 inversion. Whereas right here, we have 2 inversions. And that's because in this first case, 1 is like 2 times out of order. Notice it's on the wrong side of 2, it should be before 2, and it's on the wrong side of 3. It should be before 3. And then this one likewise, we have 3 on the wrong side of 1 and on the wrong side of 2. So in other words, we've got 2 inversions of those two. Whereas this very last one has 3 inversions, and that's the maximum number of inversions in this 3-element set setup. So let's count the inversions right there. So notice that 1 is on the wrong side of 3 and 2. It should be coming before 3 and before 2. And 2 is on the wrong side of 3. It should come before 3. So adding all those up, we get 3 inversions. But now let's tie this to what we have right here. So there's a single permutation with 0 inversions, and that seems to be the coefficient of q to the 0 in this expression up here. Because the coefficient of q to the 0 is just the number 1. Whereas notice here we've got 2 permutations with a single inversion, and this looks like it's the coefficient of q to the first power. Notice the coefficient of q to the first power is the number 2. Here we've got 2 of these single inversion permutations. The same thing is going on here. Here we've got this is equal to the coefficient of q squared. Again, we've got 2 of them. And finally, this is corresponding to the coefficient of q cubed. So we've got that up there because our coefficient is 1 in that case. Okay, so let's maybe make a guess of what's going on up here. And before we prove this guess or prove this conjecture, we'll look at a bigger example. So what it looks like is that the coefficient of q to the m in the factorial, or in the q analog of the factorial in factorial q, is equal to the number of permutations of 1 up to n with exactly m inversions. So of course we've only looked at this n equals 3 case, but this n equals 3 case is pointing evidence towards this red box fact being true. Okay, so next up what I'd like to do is briefly look at the n equals 4 case before we prove this claim. So for our bigger example, we'll look at the Q analog of 4 factorial. So let's maybe jump back to this definition so we can look through all of the details this time. So this will be 1 minus q to the 4th over 1 minus q. That's the q analog of 4. And then times 1 minus q cubed over 1 minus q. That's the q analog of 3 by this definition over here. And then 1 minus q squared over 1 minus q. And then finally 1 minus q over 1 minus q. Notice the q analog of 1 is simply the number 1. But notice each of those rational functions simplifies quite nicely. So this first one simplifies to 1 plus q squared plus q cubed. This second one to 1 plus q squared. And this last one, using a difference of squares factorization, we have 1 plus q. Okay. Now it's just a matter of multiplying that out, which isn't super interesting, so we'll just jump to its expansion. So this is in fact equal to 1 plus 3 times q plus 5 times q squared plus 6 times q cubed plus 5 times q to the 4th plus 3 times q to the 5th plus q to the 6th. Okay, so that's looking good. So what does that seem to tell us? That seems to tell us that there are 5 permutations with 4 total inversions. Well, it tells us like a bunch of other stuff as well based off of that claim, which we haven't proven yet. But I think this is maybe a nice example to look at because 5 isn't too big and finding these ones with 4 inversions is pretty straightforward. Okay, so let's see if we can list all of these. So the first one is 4, 2, 1, 3. And I'm gonna stop right here just to talk through how we know that this has 4 inversions. So the way to visualize that is to start with the numbers 1, 2, 3, 4, and then perform some swaps until we get to this. So first we can swap 1 with 2, picking up 1 inversion. And then we can swap 3 with 4, picking up a second inversion. Next up, we'll swap 4 with 1, picking up a third inversion. And finally, we'll swap the remaining 2 and 4 to pick up our 4th inversion. And that's how we can easily see that this 4, 2, 1, 3 has exactly 4 inversions. It's a permutation with 4 inversions. And now you can play this game on the 4 remaining, and what you'll see is that we get the following extra permutations with this number of inversions. We have 4, 1, 3, 2, 3, 4, 1, 2, 3, 2, 4, 1, and finally 2, 4, 3, 1. And so let's just real quick recall that that corresponds to this coefficient right here. And then maybe while we're at it, since it's fairly easy to do, let's find all of the permutations with exactly 1 inversion. So I'll put that with that orange box here. So let's see, we could have 2, 1, 3, 4. So 2 and 1 are out of place. We could have 1, 3, 2, 4. So 3 and 2 are out of place. We could have 1, 2, 4, 3. So 3 and 4 are out of place. And those are all our possibilities in this case. So as you can see, it's like easy to write them down in this case. It's a little bit trickier in the other case, although there is a systematic way to do it, which you can find online if you'd like to. We're not going to go over it in this video. Okay, so now that we've done this exploration, let's prove that claim that we had previously.
Hey everyone, before we finish this video, I'd like to take a moment to thank our patrons. The channel is possible because of their generous support. We'd like to turn off the ads on my second channel, Math Major, but to do so, we need to reach our goal of $1,000 per month on the Patreon. This will allow more people to access a higher quality experience and spread ad-free math education. So if you can chip in even a couple of bucks to help us reach our goal, go to patreon.com/michaelpennmath. or click the link in the description. If you can contribute $10 or more, you'll have your name in the credits at the end of each video. And if you can't contribute money, then please share and like this video. It really does help. Also, if you haven't subscribed to the channel, but you've made it this far, you should go click the subscribe button. Okay, back to the video.
So let's look at some notation which we might need in order to prove that claim. So let's set the number AMN equal to the number of permutations of the set 1 to n with exactly m inversions. Then the result that we'd like to prove is that the sum as m goes from 0 up to n times n minus 1 over 2 of AMNQM equals this Q analog of the factorial, so NQ factorial. Now I'd like to briefly talk about this upper bound here, which we haven't really discussed yet. This represents the maximum number of inversions of a permutation of this set. Notice this is a nice triangular number. We have n times n minus 1 over 2. Recall when n was equal to 3, we got a maximum of 3 inversions. That's because 3 times 2 over 2 is 3. When n was equal to 4, we seem to have a maximum of 6 inversions. That's because 4 times 3 over 2 is equal to 6. So this is the general formula. So maybe if you'd like, you can sketch a proof of this in the comments. It's not too hard. Okay, so now let's look at this proof. And this is gonna have like a combinatorial feel to it. So let's notice that for each sigma in Sn, and recall that Sn is the group of permutations on 1 through n, we can make n plus 1 permutations in Sn plus 1 in a natural way. So let's maybe write that out. So we can make n plus 1 permutations. So I'll enumerate them. So like sigma 0, sigma 1, all the way up to sigma n in Sn plus 1 as follows. And all of this depends on where we put n plus 1. So if, for example, we put n plus 1 at the end of our permutation, we'll create this thing called sigma 0. So let's say we'll put n plus 1 at the end. And then sigma 1 will put n plus 1 next to last in the list. All the way down here to sigma n, we will put n plus 1 at the start of the list. So let's briefly go through this via an example over here. So let's maybe go with n equals 3 and thus n plus 1 equals 4. So let's start with our permutation, which I'll call sigma, and that is the permutation 1, 3, 2. And just like in terms of this as a group, this is not a cycle. So this is the permutation which sends 1 to 1, it sends 2 to 3, and it sends 3 to 2. So you can always think about your domain as happening in order and your codomain as this, what the permutation does to it. Now we can build 4 permutations out of this, and those 4 permutations depend on where we put the number 4. So let's see. Sigma 0 puts 4 at the end, so we have 1, 3, 2, 4. So sigma 1 will put it next to last, 1, 3, 4, 2. Sigma 2 will put it next to first, 1, 4, 3, 2. And sigma 3 will put it at the beginning, 4, 1, 3, 2. Okay, good. And now let's see what this does to the number of inversions. So our original permutation had a single inversion. So I think that's pretty clear because all that's happening is we're swapping 3 and 2. Now let's count up the number of inversions that we've created. So this first one also has 1 inversion because 4 is not out of place. But now this second one has 2 inversions. And how can we see that? Well, notice that 4 is before 2, and 2 is after 3, so that's 1, 2 inversions. Then this next one has 3 inversions, And so that's because 4 is before 3 and 2, and 3 is before 2. And then finally, this last one has 4 inversions. So that means that sigma 0 will have the same number of inversions as our original sigma. Sigma 1 will increase the number of inversions by 1, all the way down here to sigma n will increase the number of inversions by n. So we could maybe track that as follows. So plus 0 inversions, plus 1 inversion, all the way down here we have an extra n inversions. Okay. So now, keeping that in mind, we're ready to write down the rest of the proof. So let's start with the sum, m bigger than or equal to 0. I won't focus on the upper bound. We could actually make the upper bound infinite, and then there are just a bunch of zeros at the end. And this will be am n plus 1 q to the m. So this is the number of permutations of 1 through n plus 1 with exactly m inversions. But notice that each of those partitions had a parent which came from Sn. In other words, it came from the partition from 1 through n. And it was created from that parent either by increasing the number of inversions by 0, 1, 2, 3, up to n. So that means we can expand this as follows. This will be 1 times the sum as m goes from 0 up to n times n minus 1 over 2, although I'll just put m bigger than or equal to 0 of am n q to the n. So this would represent taking a permutation in Sn and then just putting the number n plus 1 at the end so we don't change the number of inversions. And then we'll have plus q times the sum as m goes bigger than or equal to 0 of am n q to the m. So this represents taking a permutation 1 to n and putting n plus 1 next to last. And so that increases the number of inversions by 1, but in terms of this generating function, that is the same as multiplying by q. Now we can extend this all the way to the end, where we have the sum over non-negative m of mn q to the m, and then we're multiplying by q to the n. So that represents changing the parent permutation to the child permutation by placing the n plus 1 at the beginning. But let's notice we can factor something out of this. And in fact, what we factor out of this is essentially our base case, or our assumption that something's going on with n. So that means each of these yellow underlines are exactly the same thing, and that's the q analog of n factorial. So that's all of these. So I can factor that out. I'll factor it out of the right. So that leaves me with n factorial q, and then over on the left I have 1 plus q squared ending at q to the n. But by our definitions over here, we see that this is exactly the q analog of n plus 1. And so if we smash these two together, we get the q analog of n plus 1 factorial. But that outlines an inductive proof that this holds. Now, if you've been sticking around this long, thanks for staying. If you haven't subscribed to the channel, maybe consider hitting that subscribe button. And also, if you'd like to support the channel in a larger way, you could check out our Patreon. There's a link in the description, and that's a good place to stop.